All right, I'm back. We're on number 11 on page 301, and we're talking about velocity, acceleration, position, average velocity, instantaneous velocity, a lot of ideas. So at number 11, it says, based on the table and or your previous answers, does there appear to be a time when the car is slowing down despite always moving in the same direction? Yes, I would say there is definitely a time. There's a lot of evidence for that. We looked at the graph of velocity. We saw that velocity had a maximum. If velocity has a maximum, that must mean that there are times when the velocity is less. So the velocity would be decreasing, which means you're going slower, you're slowing down. Um, the other thing was we actually found when velocity was zero, and we found that at t equals zero, the velocity is zero. And also at like 35.0 something, the velocity is zero, which means that the thing that's moving, if it starts at zero and ends at zero, but it was positive somewhere, it must have slowed down, right? Because its velocity increased and then has to decrease to get back to zero. So I think there's a lot of evidence to suggest that. Um, so let's do the next part, which seems completely unrelated. Fill in the table of values for the car's instantaneous velocity over time. Use the derivative of s of t. So that's like, instead of using the table and approximating, we're going to use v, which is the derivative with respect to t of s. And this is a calculator thing. So let's go and do that. All right, so how can I do this efficiently? Over here, so I'm on the calculator page, I'm going to do the derivative with respect to t of s of t. And I'm going to do such that, so control equals, and then 1 to the left, such that t is equal to. So there's like a bunch of ways you can do this. I'm going to do control and then like close parentheses to get a list. And you can just do like 5, 10, 15, 20, 25, 30, 30. If you know me, you know I like to use sequences, and this is a prime candidate for a sequence. So this would give me all of these values, and I'm supposed to round them to the nearest integer. So back to the notes, I guess, and I'm going to write them down. You can copy along with me or copy them off your calculator, because I really hope that you are trying to do these things on your calculator. I can't imagine someone coming back and not knowing how to use their calculator for these things. I can imagine it, but I just don't want to see it. All right, so let's see. We got to the nearest integer, we're going to get 46. Then we're going to get 69. And then we're going to get 75. And then 67. And then 49. I have to scroll a calculator for a second. Hold on. So 49, and then after 49, I'm going to get 25. And then after that, I'm going to get 0, because I'm rounding. So you're basically at 0 when you get there. So let's see what the next thing says. How far did the car actually travel on the time interval? Well, we have a function for position, right? So we know that the distance that it traveled is going to be whatever its position is at t equals 35. So this will be s of 35. And I won't switch over, but I'm just going to on the calculator find s of 35. S of 35. 1688.7, let's say, oh yeah, so it's, which is approximately 1688.699, and that'll be in feet. Okay, so what does that have to do with anything? Well, the next question asks us to make a scatter plot of velocity over time. So I'm going to do that. Let's see. So I'm not going to make a great scatter plot. I'm just going to try to make sure that like relative heights are kind of like where they should be. So like 25 should be below 46, like that kind of thing. That's what I'm going to try for. So how do I divide by 7? Well, let's do 8. Here, here, and then here, 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 here. Okay, so this will be 4, and this would be 8, which we don't need, but it's just easier to divide something into 8 than it is into 7. And we just got to put these points like sort of where they belong. So like here, and then like 46, and then let's say 69 is here, 75 is even higher, 67 is like a little lower than that, 49 is, my scale is atrocious, 25 is going to be like way down here, and then back to 0. So this is a bad graph of v of t, like that. So, I mean, what are you going to do? All right. The next question says, draw rectangles using the heights at 5, 10, 15. So basically, do what we usually do when we draw rectangles on a graph. So let's switch colors, and let's see if we can do this. So it's going to look like this, this. And then what I'm going to do is I'm going to show you on GeoGebra I did this, because this is such a common thing to do. This is actually built into GeoGebra as a feature. So what we want to do, think about the units here. The units along the x-axis are in seconds, and the units along the y-axis are velocities, which are feet per second. So if I multiply something that's in seconds by something that's in feet per second, what units do I end up with? The units are going to end up feet per second times seconds. They're feet. So the units are feet, which means that this like region that I'm finding, this area, represents the feet that this thing has moved. It's the distance traveled. Like we're able to find, it's really displacement for those of you who are going to be picky about it. We're trying to find the displacement, the distance this thing has traveled on this time interval. So how can I write this? So the sum, well, let's find the sum. So all of them have a base of 5, which is kind of like our delta x. And then we're going to do v of 5 plus v of 10 plus, I'm going to ... plus v of 35. Okay, that's going to be approximate. So let me, I'm going to switch to GeoGebra so that I can show this to you. I think I have it here. Here we go. So I created a scatter plot. So there's a lot going on here. We have, the position function is defined, and then I found the derivative, right? So this is the velocity. And then I went through and manually put all these points in, which I wanted to do with the sequence, but I thought that there was a thing I wanted to do and I didn't do it. And so like, whatever, reasons. And then, so GeoGebra has this crazy built-in thing, which is called a rectangle sum. And so for the rectangle sum, this first one, it's the rectangle sum, S prime is the function. I told it to start at 0, end at 35. I wanted it to have 7 subdivisions, so that's what 7 is. And then if I put a 1, it's going to use, so like there's an interval from the left endpoint to the right endpoint. If you put 1, it'll use the right endpoint. So let me hit enter here, or whatever. Let me click this, and you can see this rectangle goes from 0 to 5 and uses its height here at 5. This rectangle goes from 5 to 10 and finds its height here at 10, 10 to 15 finds its height at 15. It's built in. Furthermore, it gives me a value. So I'm going to say that my summation is approximately 1654.737. Okay, so that's my approximation. Now, if we go back to the notes for a second, so GeoGebra has it built in because it's that common a thing to do. Like it's some of the stuff we do, you probably feel like, why are we doing this? Like, is this guy crazy and just making us do these things, or is there like a reason? There's almost always a reason. And in this case, when we were doing all those summations, we're building up to a bigger idea. This is part of that idea. Feet. So this is the distance traveled is approximately 1654.737 feet. Now the actual value, which we could find, was 1688.699. But this is a pretty good estimate considering that we only went 5 apart, right? Like usually we ultimately want our delta t in this case, usually it's delta x. We want that to go to 0. We want to use an infinite number of rectangles. So the next thing says to draw basically rectangles using the left edges. So I'm gonna use a different color, go back to my graph. So using the left edges, my first rectangle is here, it has no height. My second rectangle will be here. My next one will be here. and then it'll be here. This one's huge, like that. Then it'll be here, then it'll be here, and then it'll be here. Like both of them get one of the, not in general, but in this particular case, both of them get a rectangle that has 0 area. It happens. Let's go back to GeoGebra and let GeoGebra do the work on this. So let me write this down though. What we're doing is 5, and then it was v of 0 plus v of 5 plus dot 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 plus v of 30. Okay, let's see what GeoGebra has to say about this. And I know I didn't answer it. Same units, right? It's still feet. And we're still approximating the distance traveled on that interval. So let me turn this off. This rectangle sum is going to be the same. So it's s prime, which is velocity. Start at 0, end at 35, do 7 subintervals. And then the 0 means on the interval from like where you start to where you stop, use the left end point. So I'm going to press enter, and then I'm going to turn this on. Oh, I even use a color that's like almost the same. So you can see we get like a 0 rectangle and then big, big. So underestimates over here, but then overestimates over here. So it's hard to know. So we get 1653.860. So I'm going to write that down, 1653.860. So that's going to be our approximation in feet of the distance that we traveled. So back to the notes. Bouncing around. I'd love to know what people think about all this, like switching things back and forth. I mean, I have no other option, but it's not great in my opinion. So my estimate there is 1653.860. It's like a slightly smaller estimate, but it's not great anyway. So what is a better way to find an approximation of the distance traveled? All right. So what can we do? Where basically we graphed the velocity, and then we're doing our like rectangle sum thing. So why don't I say that v of t is my function, use v of t on the interval from 0 to 35, right? Okay, so I'm going to come up with a delta t. So delta t is going to be 35 minus 0 divided by n, the number of rectangles that I want to use, right? Then the height, I need a t sub I. T sub I is going to be where I start plus I times delta t, which in this case is just going to be 35i over n. I need to find the heights. So the height will always be v of t sub I. And what I want to do is I'll find the velocity, usually I'm finding, so this is area actually. So area as a function of n is going to be the sum from I equals 1 to n of v of ti, which is the height of the rectangle, times delta t, which is the base. You do base times height. And then what I want to do is the limit as n approaches infinity of a of n. And let's see what we get. We could have called that d for distance or displacement. But we didn't. So, you know, poor choice probably on our part. But we're finding the area. The area bounded by the velocity curve is going to be overall your distance traveled. If velocity is always positive, it's your distance traveled, I should say. In general, it's your displacement, but we don't need to get into that just this moment. So let's go back to the calculator. And here we go. We're going to do this. All right. So this is what I got exactly when I just did S of 35. Let's see. So we are going to do, I need the derivative, which I'm finally going to define. I'm going to say v of t is, let's steal this, the derivative with respect to t of s. Okay, so a of n is going to be the sum. So this is a lot of ideas coming together. I goes from 1 to n of v of t sub I is 35i over n times delta t, which is 35 over n. Okay. Now we want the limit as n approaches infinity. Infinity of a of n, and let's see what we get. So we get 1688.69925. Does that look familiar? Does that look like S of 35? It does, because these two processes are the same. If we can find the total accumulated area between the horizontal axis and the velocity curve, that's going to tell us our ultimate change in position, so our displacement on a time interval, which is a big, big idea. I'm going to go back to the notes. I'm going to fill in this number, and then we'll be done, because we don't want to talk about this for hours and hours, which we totally could, because it's one of the bigger ideas. But there's like a weird connection between velocity and position and the area bounded by a velocity curve. So this gave us, I forget what it was. It was just so startling. 1688.699, which is actually equal to, in this particular case, S of 35. And that was crazy. That was like a long way to go to get here, but that was what we wanted to do. So we could do this and get the perfect time, assuming we have a function. If we don't have a function, we're going to have more problems. But we had a function, so we were able to do it. All right, so I'm going to stop this here, come back in the next video, keep going. Hope you're finding these helpful. See you then, and goodbye.